One standard related rates application that you see often is objects moving in such a way that makes a triangle. This is one such example. Two cars start moving from the same point. One travels south at 60 miles per hour and the other travels west at 25 miles per hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so step one is to deeply understand the exercise. And it really helps to draw a figure to help understand what's happening. So here's our starting point. We have one car moving south at 60 miles per hour. And we have another one moving west at 25 miles per hour. So let's call this east-west distance x and the north-south distance y. And what we're interested in is the distance between them, which we can call z. So here I have a pretty good idea of what's happening. These two cars are moving in 90-degree directions from each other, and the distance between them is increasing as they keep driving and driving. Let's write down what's given and also what our goal is. That's a good way to keep track of all this. So given, we have dx dt is a constant speed of 25 miles per hour, so I'll write that as miles per hour, and we have dy dt, that's the rate north-south, 60 miles per hour. And our goal is to find dz dt, the rate at which the distance between the two cars is changing, but when, that's always important for our goal, at t equals 2 hours. Let's check in with our steps to see where we stand. Okay, step one is done. We understand the problem, we have our diagram, we have our givens and our goal. Step two, we need to write an equation that relates the various quantities. Here, I think we're going to veer a little bit. It says, if necessary, use geometry to eliminate a variable. We can do this without eliminating a variable. You don't always have to eliminate a variable in step two. You can just jump to step three sometimes and be just fine. Use the chain rule to differentiate both sides. So let's do that in this case. Can you think of an equation that relates x, y, and z? You may have thought of the Pythagorean Theorem, x squared plus y squared equals z squared. And we can jump straight to the derivative. 2x dx dt plus 2y dy dt. I'm using the chain rule because we're taking the derivative with respect to t instead of x, y, or z. So equals, and we have the chain rule one more time, 2z dz dt. And now we can solve all of this for dz dt. I'm just going to divide everything by 2z. That gives us 2x dx dt, lots of writing for these, plus 2y dy dt, all over 2z. And we want all of this evaluated at t equals 2 hours. Well, we know what dx dt and dy dt are. Those are given. We just need to find x, y, and z, which we can do. Oh, and look, the 2's cancel out there as well, so that's kind of nice. 2, 2, 2. Save us a little bit of time. Well, we know the speed, so we can compute the distance after 2 hours. So let's see here. X equals 25 miles per hour times 2 hours. That gives us 50 miles. Similarly for y, we have y equals 60 miles per hour, okay, times 2 hours again, which gives us 120 miles. So there we have x and y. We just need z. Well, we have this Pythagorean theorem relating x, y, and z, so we can solve for z. Let's take only the positive value. Z equals x squared plus y squared, square root of that. All right, square root of 50 squared plus 120 squared. That comes out nicely, turns out to 130 miles. So now we plug everything into this dz dt equation. So dz dt finally is, okay, so we have x, so 50 times dx dt, 25, plus y, 120, dy dt, 60, all over z, which we now know is 130. Computing all that out gives 65 miles per hour. The last thing we do is ask if 65 miles per hour is a reasonable answer. And it is. You have two cars traveling, one at 25 miles per hour, one at 60 miles per hour. So 65 miles per hour is around what we'd expect for the distance between them. I'd be concerned if it was 1 mile per hour or 300 miles per hour.